Hello everybody, my name is Shijian. I'm a PhD student at Worcester Polytechnic Institute. Today I'm going to present our work Perseus, Characterizing Performance and Cost of Multi-Tenant Serving for CN Models. This work is the collaborative effort of Matthew, an undergraduate student, also at WPI now graduated, me, and our advisor, Professor Tian. In this work, we explore the multitude of deep learning model serving settings and ask the general question of what is the benefit of doing multi-tenant model serving and how can we do it better? First thing first, what is model serving? And more importantly, why do we care about it? Model serving in the context of our work means providing trained deep learning models for inference as a service. Nowadays, end-user applications powered by potent deep learning models are becoming an inseparable part of our lives. Take our target workload, the convolutional neural networks, for example. CNNs are widely used in tasks like object detection, face recognition, and so on. To consolidate this notion of model serving further, we examine the deep learning pipeline and how model serving is typically handled in the cloud. When we talk about deep learning, there are two essential stages involved. The first one is training, where you go over iterations of feed-forward and back propagation to obtain an ideal set of model parameters. And then you take the trained model to inference, the second stage. This is where you use this model to do all sorts of tasks. Typically, to ensure the availability and scalability of model serving service, the models are hosted in cloud data centers. End users coming in with their mobile devices send requests to the cloud, and in return, after inference, the results are sent back to the users. So this whole process here is model serving. Since we are dealing with the cloud, there's one thing we all care about, the cost of running the cloud virtual machines. So how exactly can we achieve cost-effective CN model serving in the cloud? The number of cloud VMs we rent and how long these VMs run the service both determine the price we have to pay. And since model serving is usually a long-running service, intuitively we want to maximize the utilization of the VMs, or maximize the inference throughput to minimize the cost. To reach this goal, one very important step is to understand and characterize the intricacies and trade-offs of different model serving deployment settings so that we can know what the best hardware platform is for serving a specific model. And furthermore, how do we actually deploy the model for the most cost-effective way of serving? Now you may ask, why is this hard? Don't we just put up a cloud VM and put the CN models there? Unfortunately, there's much more to that. There are myriad types of cloud servers out there, and more importantly, the ever-increasing popularity of hardware accelerators introduced an extra dimension to the problem. The most widely used hardware accelerator in the cloud is the general-purpose GPUs, which is one of the focus of our work, for it is usually faster and more suitable for highly parallel tasks such as deep learning. So all these different types of servers have different prices or even pricing policies. For example, GPUs are orders of magnitude more expensive than CPU or memory. And on top of that, all these different types of servers can perform in a drastically different manner. This is not to mention that the serving performance and the cost on the same hardware can vary a lot, depend on what model you're serving. Say if you have a tiny model served on a monstrous machine, that's an overkill and might not be smart economically speaking. Last but not least, we can serve up the models in various ways of deployment. In the cloud, we don't have infinite resources. If we do it smartly, we can save up cost, and if we don't, we might end up paying more. With that said, here's an overview of our work tackling this problem. First and foremost, we designed and implemented a suite of tools collectively referred to as Perseus. Perseus allows us to do evaluation of performance and cost profiling in a streamlined fashion. It also provides insight to performance and cost trade-offs for new model serving scenarios, such as running new CNN models on different GPUs. Facilitating Perseus, we were able to gain insight on a couple of key questions. The first one is that what can we say about different hardware used in model serving and what their impacts are on the cost and performance of the serving? The second question is, given a hardware configuration, how do we deploy the models to maximize performance and minimize the cost? Let's take a quick look at the architecture of Perseus first. The core functionality of Inference is handled by NVIDIA TensorRT, which runs the request sent from the client servers. Containerized Node Exporter and C-Advisor provide raw performance metrics for the monitor. The monitor is mainly handled using Prometheus and visualized with Grafana running on Caddy servers. And we glue together the components using REST API and gRPC. All components are encapsulated in Docker containers to ensure reproducibility. You can visit the linked URL to access the Perseus codebase. Now that we have introduced the background and the toolset used, we dive into the questions stated earlier. The first question we look at is, what is the cost and performance implication of serving with CPU versus GPU? Here is the setup for all our experiments. We used two vastly popular CNN models, ResNet 50 and Inception v3, both trained to do object recognition tasks on the ImageNet dataset. They are structurally different but similar in size. The entire testbed was deployed on Google Compute Engine, which is one of the mainstream cloud computing services, alongside Amazon EC2 and Microsoft Azure. We used two GPU types built for inference that GCE provides, NVIDIA P4 and T4 GPUs. Both are advertised to be optimized for deep learning inference. There are two key metrics that we mainly care about: peak throughput of the inference and the cost we pay per million inference requests. There are in total 3 deployment scenarios: serving with CPUs, serving with GPUs, and for GPU serving, we explore the options of dedicated or multi-tenant serving. Alright, what are dedicated serving and multi-tenant serving? We know that the GPUs have very limited memory size, so the intuitive action we want to do when doing model serving is to have a single model to be hosted on a single server. On the other hand, multi-tenant serving is the practice where we put more than one model onto a GPU server, so hopefully we can squeeze whatever is left with serving one model and use that to serve other models. With that said, let's look at the experiment results next. First, we look at inference with CPUs versus GPUs. The question is, why do we need GPUs in inference, and how good they are compared to the traditional CPUs? If we look at the ResNet 50 inference, for example, on a model hit, it is on average 8.7 times faster to execute on GPUs. But on a model miss, not only is the overhead for GPU inference much larger, the overall execution time on GPUs becomes much larger than the CPUs as well. The reason for this is that a model hit means that the model was already present in memory, either the main memory or GPU memory, so it can be executed right away. But a model miss means that the model first needed to be loaded from the disk. When using CPU for inference, the model goes from disk to main memory, and when it comes to GPU inference, the model needed to be loaded from disk into main memory first, and then transferred to GPU memory to be executed. The reason for the GPUs to perform much worse on a model miss is because these multiple levels of memory transfer overhead, and they can be really slow. Now we continue with our observations. Even though the on-disk sizes of these two models are roughly the same, it takes twice as long to load Inception v3 into CPU memory, but nearly the same amount of time to transfer each model from CPU to GPU memory. So this result demonstrates certain benefits of masking memory transfer time between CPU and GPU based on the model size, and the benefits of in-memory model caching in general. It is not always faster to execute the model on a GPU though, even with GPUs optimized for inference such as NVIDIA P4 and T4 GPUs. For example, in the case of Inception v3 on a hit, it is more than 3 times faster to execute using an Intel CPU than T4 GPU. It may seem that some models are more suitable for CPU serving. However, keep in mind that this was done with inference batch size of 1. Alternatively, we measure that the peak throughput of both GPUs to be at least 12 times higher than that of the CPU using a batch size of 8. Great, now we know the GPUs are pretty good for inference tasks. The next question is, what is the cost and performance implication of dedicated versus multi-tenant serving? In other words, how do we effectively utilize the GPU resources? Here's the results of model serving on P4 GPUs. The terms we define here are cost per million requests, 95th percentile latency, and the peak throughput of inference. Serving with 2 P4 GPUs can be 18.4% cheaper for 1 million requests due to CPU cost amortization and linear throughput scalability. Also, the 95th percentile latency is decreased with 2 GPUs. Similarly, increasing the number of T4 GPUs from 1 to 2 decreases the cost and latency of inference, and increase the peak throughput across both models results in 37.7% cost saving. So, in general, it is better to have more than one GPU in serving when the request rate is high. More importantly, we also found out that in dedicated serving, the GPU memory is underutilized, and this utilization can be improved potentially by using multi-tenant serving. So that's good news, right? You might think we can use whatever is left of serving one model to serve the other model. Unfortunately, it's not that simple. Let's look at the cost per million requests under a different light. Again, we're taking P4 GPUs as an example. Since we only have a fraction of the GPU resources left, that said, we are already serving one model. The peak throughput of the co-hosted model usually cannot be optimal, and lower peak throughput can actually lead to polynomial cost increase. Take ResNet 50 for example, as you can see along the red lines. The lower the throughput is, the higher the cost will be. And it doesn't follow a linear trend upwards. It's actually worse. You might think, maybe if we can somehow achieve peak throughput for both models, then the cost can't be that bad, right? Now let's examine the throughput we can achieve with multi-tenant serving. Each group of bars represents a hardware configuration to serve the models with. The first and third bars of each group represent the single dedicated model serving throughput, where there is only one model being hosted on the server. The second and fourth bar denote the multi-tenant counterparts, where both ResNet 50 and Inception v3 are hosted on the same server. We approach peak throughput for one model, then send in requests for the other model. Take the fourth bar for example. We first saturate requests for Inception v3, then process however many requests we can for ResNet 50. We see that inference on T4 GPUs generally has higher throughput than P4 GPUs, either with 1 GPU card or 2, as we expected since T4 is the more expensive type. More importantly, however, we observed that A multi-tenant model serving with extreme workload mixes, in this case it's a 1:20 ratio, can achieve comparable throughput to a dedicated single model serving with one GPU. However, in the case of two GPUs, the aggregated throughput of multi-tenant model serving slightly lagged behind, especially in the case of serving ResNet 50 as the bulk of workload. So extreme workload mixes don't necessarily mean higher throughput. And remember, as the throughput gets lower, the cost per million requests is going higher. In other words, multi-tenant serving, when done poorly, can actually cost more. So how do we deal with this? We could change the workload ratio of the hosted models. Here, the y-axis represents the workload we send towards the inference server for Inception v3, while the x-axis represents that of ResNet 50. The results show that it is a nonlinear relationship as the requests for two models change, shown in the figure as the dashed lines. It can be observed that the performance gain of exploiting underutilized resources can surpass the overhead of hosting an additional model. The performance gain occurs when the throughput for both models is consistently achieved and both models are experiencing non-trivial workloads, for example between 25% and 75% of their peak throughput. Furthermore, we observe that the cost per inference and latency decrease when the number of GPUs increases, leading to up to 12% cost saving. To conclude the talk, here are some takeaways for this work. The first takeaway: we found out that there's insufficient framework support for CPU inference and model caching. As we said earlier, the memory transfer can be very expensive, and a proper caching or masking for memory transfer process can go a long way in keeping the execution time low. The second takeaway: counterintuitively, we found out that using more than one GPU card for serving can actually save the cost of operation of running cloud inference servers. Takeaway 3, we found out that properly using multi-tenant serving on GPUs can further reduce the cost of serving to up to 12%. However, this must be done properly by keeping the workload ratio within a less extreme range. That's all for my talk today. Thank you for listening. Thank you for tuning in. If you have any questions, please reach us in the comment section. Stay home and stay healthy. Let's get through these perilous times together.